Okay, this very short little video here is going to talk about dielectrics and the role they play in constructing and using capacitors. So if you want a large capacitor, what you want to do is increase the area of that or decrease the distance between the two plates. But if D gets too small, the electric field gets very small, right? Because your electric field is your voltage, which is your voltage of your battery, divided by that D. And this can actually break down. So just like lightning, well, lightning happens because you have a huge charge way up in the sky, and then you have a ground charge on the Earth. The air in between those two charges is a very good insulator, but at some point that electric field becomes too strong and it does something called ionizing. Basically, some of the molecules are transformed into ions, and all of a sudden they become a good conductor, and you get a bolt of lightning. Well, the same thing happens in a capacitor on a much smaller scale. You have a small distance there and that voltage gets large enough, it'll ionize the air in between, and the charge all of a sudden will jump from here to there and it will totally discharge your capacitor, right? It's not what you want to happen. So we have we can define a level at which that happens, right? This is volts per meter. So that's the strength of that electric field, volts per meter here. When that gets too big, it gets above that, then you're going to discharge accidentally your capacitor. So one way to get around that problem is to use what's called a dielectric. This is an insulating material that's in between your two plates. And this does two things. First of all, it increases the breakdown point of the field. So we just said, there's a point at which air is going to ionize and your capacitor is going to accidentally discharge. Different materials have a different dielectric strength, and you can see that over here. So air's is 3 million, right? While other materials are as high as 24 or 60 million. Okay. The other thing you can do, so all that does is keep the capacitor from breaking down. You can also increase the capacitance by the dielectric constant, and again, this has to do with the material that's in between the two capacitors. So we take that equation for capacitance, which we were assuming a vacuum. So our value of kappa was 1 in our earlier equation. So we can add this value of kappa, which can be as high as a couple hundred, and that's going to increase the capacitance of our material. So that can make your capacitor a lot more stable and a lot more highly powered. More complicated is the dielectric. Why is a dielectric increase capacitance? Well, in this case, you've got a positive charge here and a negative charge here. You've got an insulating material here, so there's no conduction of material here. But you do have a really strong field, and that's going to polarize the molecules in your dielectric. So what happens here is polarization of the molecules means that the negative part of the molecule is going to be pulled times the positive is going to be pulled times the negative. So it's not moving them around, but it is creating a really strong negative or electric field right here, right? Because those are close together, and those are really close together. And when that happens, we know from Coulomb's force that in decreases with the radius, right, with the distance between the two charges. So the fact that these two charges are really close together, even though it's only a polarized part of the molecule, right, it's not all of that, it's not all of the charge that is over here, it's not as strong as that. But the fact that it's closer makes it very powerful. And so that strong attractive force between this part of the polarized molecule and here pulls more charges onto that positive plate.